Okay. So now I sent out an email to each of you informing the grade for your class quiz one. Have you noticed the email?
Yes, Dr. Ali.
Yes, Dr. Ali.
Okay. Right. So I will be going over that little bit. And then today, because um, your exam is in next class, so today I will not cover that new thing. Uh, I will be discussing those quiz and then few other questions, and then you will be ready to go. Okay, so I noticed that everybody, that incorrectly did number five. So first I like to discuss that one. You see, class quiz question number five. So this should be the correct result. R value should be 0.12 ohm. Therefore, I think I noticed some of you were close to this one, 0.14, but still your approach is wrong. You have used the voltage. But in case of the series circuit, you cannot use the voltage. See this one? A 10 MVA, 5000 ampere, three-phase Y-connected synchronous generator with a zero point 0.9 power factor employs a series dynamic braking resistor. So this means this is series connected. This means that for each phase, for each line, there is on braking resistor in series. And then because Y connected, so the line current and phase current is the same. So therefore everybody see, this 5000 ampere, this is the rated current, right, for this generator. But of course, this is the line current. But because this is the Y connected, the line current and phase current is the same. So this means in all of the three phases, this current is flowing. And what it says, during fault, if the series resistors consume the power which is equal to the machine's rating, then calculate the per phase series resistance value, assuming the rated current flows through the line during the fault. So we are assuming that, okay, that is the maximum current that flows through the line. So therefore, that is also clearly mentioned. So this means first assume that in each line that current flowing. And there is a resistance in each phase. What is doing? The power consumption is equal to the machine's rating. So therefore, you see 10 MVA is the machine's rating. Of course, this is three-phase power. So if you convert into watt, then you have to multiply it by 0.9. So therefore, everybody see 10 MVA multiplied by 0.9, you are getting 9 megawatt. So but that is the total three-phase power. So therefore, of course, this is the balance system. So for each phase, you are getting 3 megawatt, 9 megawatt divided by 3. So why we are doing that? Because you are asked, calculate the per phase series resistance. Now, in series, for each phase, this current is flowing. So therefore, I square R equal to 3 megawatt. So and then find out the R. And what is the I value? I value is this one, 5000. So therefore, you should be getting 0.12. So I noticed some of you, what you did, you calculated the voltage by using this equation. But you see the voltage is always between 2 points, right? Phase to neutral or line to line. So therefore, even though you say phase to neutral, but this resistance is in series. So therefore, for series circuit, current is applicable. Therefore, you will be using the I square R for series circuit. And then you will be using the V square R in case of the parallel connection, parallel collected resistor. That time V square over R. So that's why you got different results. And then some of you did completely different way. So is everybody fine with this one?
Yes, Dr. Ali, but I have a question.
Sure.
How many points about you have on this point in this question?
Oh, so therefore what I did, for every question 3, and for question number, sorry, just a moment. How many total question? Total 7, right? For every question, I allotted 3. For question number 2, I allotted 2. So in that way, total 20. So this means question number 1, 3, 4, 5, 6, 7, each 3 credit. and question number 2 is 2 credit. So in that way, total 20. So therefore, depending on situation, I have got. So therefore, this is in your cases, this is in everybody's cases, this is completely wrong. But still, I have given you some credit, maybe 1 or 2, like that.
Oh, I think the only problem I have here, I forgot to divide by 3. So I used this equation, r squared times r, I squared times r equal, instead of 3, I put 9.
Yeah.
This is the only mistake I
Yeah.
did.
So therefore, you see, it is then calculate the power
Yes.
page. It is clearly mentioned.
Yes, sir.
Yeah,
Thank you.
I noticed. I noticed your case.
Mhm.
Mhm. So, and then Venkat, I think you left it blank, right?
Yeah, yes, sir.
Like everybody attempted, but why did you keep it blank? Yeah. Okay. Anyway, so is there anybody other questions and comments? So therefore, you say those who use the voltage, you cannot use the voltage because this is series. So for voltage, you know that one voltage between 2 points. So therefore, even line the neutral, there should be the element between that point. But it is not that line to neutral. It is series connected thing. So therefore, you must go through the I. I mean, that is the significance of current and voltage. Current is for series. Voltage is for parallel case. That's why there are two equations, I square and V square over R. Okay, so that is fine. Now this one, everybody see the question number 1. I mean, everybody tried to explain, but you explained something different way. You look the efficiency. So the basic definition of efficiency for anything on any machine on inverter, output by input. But what is the input? Input is again output plus losses. So therefore, you have to tell that if you control the reactive power, you see the question was how can the efficiency be improved by controlling reactive power? You have to tell that if you control the reactive power, this means if you reduce the reactive power by improving the power factor, then your losses will be decreased. So therefore, if you see the efficiency equation, output over output plus losses will be decreased. Consequently, the efficiency value will be increased or improved. So is everybody fine? Could you follow me?
Yes, Dr.
Yeah, so I mean, you explained that thing that we have to control the reactive power, we have to improve the power factor, but what it does, by improving the power factor, what you are doing, you are reducing the current, you are increasing voltage and you are reducing the current magnitude. Consequently, your losses is getting reduced. I square R loss, I square X loss, both reactive and active power losses is getting decreased. So consequently, your denominator value, efficiency is output over output plus losses is getting decreased. And that is the reason of controlling the reactive power, even though it is of no use, because it just causes losses and losses in the system. Consequently, we get low efficiency, poor voltage regulation, and higher loss. Okay, so, and then question number 2. So you remember that day we were discussing the, I think although it is long ago, I think second class. In this case, you know, the assumption is that you have AVR, governor, PSS, everything is equipped with the generator, but still it is oscillating around the synchronous speed. And this might happen because, you know, continuously consumers are changing their load, either injecting load or taking out load, whatever the amount is, 100 watt, 200 watt, either putting or taking out, it is continuous. So consequently, always the impact is going on the shaft, on the speed. So that's why if you use the damper winding, then damper winding can eliminate that effect. And probably you remember we told that that effect, that oscillation around synchronous speed of synchronous generator is called the hunting effect. So therefore, to reduce, to eliminate, or to remove that hunting effect, you have to put the damper winding. Therefore, the appropriate answer would be that by adding damper winding, those oscillations on the synchronous speed can be removed. So therefore, can you please everybody write down the answer? That by adding the damper winding. So I think each of you know this thing, that damper winding has two roles. For synchronous generator, damper winding is used to eliminate hunting. Hunting is oscillating around synchronous speed due to change in load by the consumers. That thing is called the hunting. And to reduce that oscillation, you need the damper winding. But for synchronous motor, damper winding is used to initially start the motor, synchronous motor. You know, synchronous motor is not self-starting due to its inertia. Now, to get it initially run, you need some starting torque, and then damper winding is used to initially give some torque. So therefore, damper winding in synchronous machine has two roles. For synchronous generator, it eliminates hunting, and for synchronous motor, it's provide starting torque. So therefore, you have explained something. I have assumed your answer, but the answer was not appropriate.
Dr. Ali, I have a question.
Okay.
But I mean, this damper coil is already incorporated during the construction of that machine, right? It's already there, or you just put it externally?
There is some sort of controller there. There is controller there.
So does it come with the generator, or we have to, I mean, externally add it?
No, that is come, but it is automated. For example, that is the thing. Like at the start of the synchronous machine, damper winding will help you start. Then once the motor has started rotating, then it will be taken out from the circuit. It will be taken out. It will be not available in the circuit. It will be disconnected from the circuit. Now that thing is automated.
Yes, but it is also part of the synchronous generator, right? It comes with that, right?
Yeah, so you can say that is the part. So that is the question, yes. That what is the way or how you can remove that oscillations.
Okay, I thought like it is already there, so we didn't have to think about that.
Yeah, no. So that is the thing, that what you can do, what you can put. Now the thing is that if this oscillation amount is too much high, then even the damper coil is not enough. Then you have to put some other external means. For example, energy storage system or other compensators, some filter. That is the other things. It depends on how much is the oscillation, what is the magnitude of oscillation. So in this case, when I'm saying around synchronous speed, this means that it is not always going high. It is a little bit coming down, but it is vibrating. So that
Right.
thing is called the hunting, and then to remove that oscillation, that you need damper winding. Okay, so the number 3, for the transient stability improvement of a power network, how can you coordinate the operation of a series dynamic resistor and static synchronous compensator? Now, here again, you see the difference between this. I mean, you all explained what is the function of this on and this on. You said that SDBR can control active power. Then you said STATCOM can control reactive power. I mean, that is correct. That statement is right. But you see, this is the series device. It is connected in series. And then STATCOM, this is a parallel connected device. For example, the braking resistor that we learned in the class, mostly that is the parallel connected. Unless it is specified, it is series dynamic braking resistor. Now, here is the thing, here is the difference. Series connected device, I mean, not only for SDBR, for other fault current limiter, or if you connect a capacitor in series, that is, because that is connected in series, it is a current dependent source. And when a parallel connected device, that is voltage dependent source. Now the question is for the transient stability improvement, meaning that the fault happened and you want to coordinate, meaning that you want to put both devices, but not simultaneously. Now you can argue that what is the wrong if I put both simultaneously, like fault happened and then I connected series device. Also, I inserted the STATCOM with the controller. You can do that, but can you guess what is the problem? Because this is parallel connected device. Parallel connected device is dependent on voltage. Unless there is required voltage, the thyristor or IGBT diode, those cannot operate. Because during fault, here is the thing, during fault, voltage has gone almost zero. Therefore, with that very low voltage, parallel connected device cannot operate. But the series connected device is fine because series connected device does not depend on voltage. Even though during fault, at the fault point, voltage has gone zero or close to zero, or there is some value, but the current has increased. There is significant amount current, which is fault current. So that's why what you have to do, once the fault happened, immediately you have to insert the series resistor so that it reduces the magnitude of fault current. And you cannot but wait until the circuit breaker opening. You see, once you open the circuit breaker, this means that your current is not important. You reduce the magnitude of current, but then there will be voltage. You see, the circuit breaker open, but there will be voltage in the circuit. And with that voltage, the STATCOM will operate. So that's why the coordination means you have to tell that series connected, series dynamic braking resistor will be initiated right after the fault, and then after circuit breaker opening, STATCOM will come into the circuit. And the same thing happens, in fact, all parallel connected device, energy storage, your SBC, synchronous condenser, any parallel capacitor, then braking resistor. Everything actually comes into operation after circuit breaker opening, because that circuit breaker opening time is not big, maximum 5 cycles. So the one circuit breaker is open, then there is enough voltage because you opened the breaker. So now you disconnected, you break the current. That's why it is called circuit breaker. But now there is voltage, and that voltage is now enough to operate the STATCOM. Everybody, could you follow me?
Yes, Dr.
Yes, yes. So therefore, I mean, I gave you credit. I mean, most of you have written that, okay, first SDBR and then STATCOM, but I am telling you that engineering reason that why this is first and why this is later. Therefore, as I said, you can argue, I mean, you can set the controller such a way that STATCOM will come immediately after the fault. That is possible, but it will not work unless the circuit breaker is open. Even though by force you connect it right after the fault, but because it is parallel connected, it depends on the voltage. So therefore, there will not be enough pulses, voltage pulses, to trigger the thyristor or IGBT, whatever the inside of the STATCOM. Those power electronics device will not be activated unless it gets the required voltage. That's why it is better not to insert immediately after the fault. Wait until the circuit breaker opening. Okay, so this one, like number 4, during a network fault, while both the voltage and real power of a synchronous generator drop, but the speed increases. Explain the reason why generator speed increases. So therefore, you say, I mean, you explain the reason um, voltage drops and then how the real power goes drop. You explain that torque, speed, and omega relationship. That is fine. But then if you just look that swing equation, phi A equal to Pm minus P, so during fault, P goes 0. And then system gets accelerated. So that acceleration goes in terms of the speed increase. So that is the reason. So therefore, you just need to tell that during the fault, so even though the voltage real power goes down or drops, but speed increase because the system get accelerated. So system means in this case the shaft of the generator that gets accelerated, and that acceleration causes the speed go high. So is everybody fine?
Yes, Dr. Ali.
Yes, sir.
I mean, everybody have tried your best to explain. Those are partially correct, but the appropriate answer is that if you look that swing equation PA equal to PM minus PE, we are assuming that there is no disturbance on the mechanical side. I mean, of course, you can argue that anytime there can be disturbance. That is different thing. That mechanical side had stopped. No fuel is coming. That is different thing. Then instead of increasing, like system will stop. No power production. That is the emergency situation. That is different. But the context of this question, we are assuming that mechanical side is intact. That is fine as it is. So, but because PE goes low, system is getting accelerated. There is high positive value of PA. And that acceleration means that goes on the shaft system. Okay, and then we explain this one. Number this one. How does a synchronous condenser differ from a static synchronous compensator used in power network? So therefore, most you have written this one. These two are fine in most cases. I mean, what is the context of this question? Both can control the reactive power. I mean, synchronous condenser that works as a capacitor under certain condition, under overexcited mode when there is no mechanical load. That all of we have told, that's correct. Even the synchronous STATCOM, that also can compensate the reactive power. But the difference is that static synchronous compensator is a static device. It does not rotate. On the other hand, synchronous condenser is basically the synchronous motor under a special situation. So therefore, that is the difference, that this is a rotating and static synchronous compensator is a static. That is the difference. But both are the reactive power control sources or devices. And this on the transient stability of a power network is evaluated by observing the active reactive power profiles. This means you look that what happened. Is the active power going low or reactive power is going high? And by looking that profile, you judge the transient stability. On the other hand, the power flow or the load flow also deals with the active reactive power flow. So what you do with the power flow or the load flow, you basically analyze what is the power flow, active power flow, reactive power flow, what is the bus voltage at specific branches or the internet, or that you look. Then how does the transient stability differ from the load flow? So therefore, as you know, the transient stability, that is for only transient situation, only during the fault. So period of interest is only 5 to 10 seconds. On the other hand, the load flow is for steady state. So that is the difference. So you need to just simply tell that although load flow deals with active reactive power, but that is for the steady state condition. And then transient stability for transient condition only. Period of interest is only 5 to 10 seconds or maximum 20 seconds, not more than that. So everybody, could you follow me?
Yes, Dr. Ali.
Okay.
Yes, sir.
Yeah, so please note down. Therefore, I have accepted most of your my answers, graded, but I think the most, that math part is number 5. You did completely different way. And sometimes number 4 and number 1, like you wrote different way. I mean, even though you understand, so I understood that you understood, but still you wrote like differently, like number 1 and number 4. And the last two was, in most cases, it was fine. I mean, you properly, that's why some credit was cut. Okay, so as I said that today I will not go long way, just few more questions, and then you're ready, and then everybody please look this carefully and be ready for the exam. Here you see few theoretical conceptual question. Everybody see. Assume a severe fault has happened nearby a generator connected to a large power network. So there is a large power network that has many generators, but the fault has happened nearby a generator. Now, you see, last class we are looking at optimal reclosing technique. Now, according to the optimal reclosing technique or that principle, we learned that the point when the total kinetic energy oscillation of the generators without reclosing operation becomes the minimum should be considered as the reclosing instance, right? So therefore, for example, either this point or this point or this point. So it is that minimum point that we learned. Sorry. Now, for this reclosing approach, is there any issue with using only the speed profile of the generator nearby the fault, as the speed constitute the kinetic energy? I mean, what I am asking this one, see the question, that for this reclosing approach, that instead of that total kinetic energy response, if I just look the speed profile of the generator nearby which the fault happened, what is the issue? Because I am arguing that speed constitute the kinetic energy. So kinetic energy means like half mv square, right? Half gi omega square. So therefore moment of inertia is constant. That information is given, you will get from the machine rating or nameplate data. You just need to capture the speed information. And if you plot the speed information, for example, here it is plotted total kinetic energy versus time, exactly you will see the similar pattern of the speed. You see, we learned that during for speed increases and then decreases and oscillation and then settle down. And because this kinetic energy is calculated from the speed, so therefore speed profile also look like that one. So but then speed will have also the minimum point. So that's the question, that what's wrong? Because you see, this is the total kinetic energy and then there is omega m. That omega m is that speed. So what is wrong, or is there any issue with using only the speed profile of the generator nearby the fault? And then also I am emphasizing, because the fault happened nearby a particular generator, at the very first sentence I am telling. So what is the issue if I take the speed profile of that specific generator and plot this way and try to get the minimum? So will it not give the same level of stability? What is the issue? So what do you think?
I think it's if we just control it locally, then there would be problem in synchronism.
So what is the problem? Problem will come in what sense? From where the problem will come?
So because if we take the kinetic energy, we have to take total kinetic energy of all the generators running in the grid, right?
Right.
So if we just take the speed locally, I mean, for one generator only, then we are only taking care of that generator. We do not care about the synchronism between different generators.
Right. So exactly. That is the thing. Therefore, for example, everybody see this is a power network. It is called IEEE 30 bus power system. And here you can see the 1, 2, 3, 4, 5, 6 generator. And then, for example, fault happened near G1 or G2. And then, of course, if you take the speed, it will control something. It will do. But you are not taking into account the other generators. This means when you are using the only speed information of that local generator, locally it can control. Probably that particular generator might be stable, stability might come back, but you are not looking the other generators. What is their status? So that is the reason that, like Manoj said, so that's the correct answer. So therefore I am asking that, is there any issue with using only the speed profile of the generator nearby the fault, as the speed constitute the kinetic energy? So you have to tell, although the speed constitute the kinetic energy, but considering the speed profile of a particular generator, meaning that that can control only that generator. because you are not taking any information from other system, from other generator. Consequently, that generator might be stable, but the remaining network might be still unstable or oscillating. So that is the issue. And that is the reason, going back to that total kinetic energy oscillation, that is the reason. If you see total kinetic energy, meaning that this profile includes, it captures the information of all generators. It is taking into account all information. Consequently, the minimum point that you are looking, this means this minimum point that is capturing information of all system. Versus, you might get the similar response when you will be looking only speed information of generator, but that minimum point might not be the accurate or the correct minimum point or optimal minimum point. Because now you are looking the minimum point here, 0.89 or 1, but if you have the speed, probably it might be too delay. Maybe at 2 seconds you might say. So that might be too late. So therefore that local generator might be safe, but other generators might not be safe. That is the difference. So everybody, could you follow me?
Yes, Dr. Ali.
So therefore, in other words, in a large power network, in an integrated power network, always it is better to use a global variable that will capture the information of all the power sources in the system. That will take into account the effect of all the sources, because even though the fault is nearby one generator, but other generators more or less are getting affected. Yeah, and more or less it depends on the inertia. How much is the inertia of the other generators? If their inertia is very low, then they will start spinning very fast. That you have to control. That's why the capturing the information from all power sources in a power network is important. And that is the reason going from speed profile to the total kinetic energy. Okay, so everybody, can you see this one? We did on similar thing. Assume that on a 345 kV three-phase transmission line of a 50 Hertz power network, a three-phase to ground fault has occurred. The circuit breakers on the line operate properly under fault condition. What should be the required reclosing time of the circuit breakers, allowing the deionization of the faulter? So what should be the value of the reclosing time? What should be the instant?
I got 0.41 second.
Yes, that's right. So everybody got the same number? This means that, you see, as we are discussing, this is on empirical formula, circuit breaker um, reclosing instant. That this means that you must wait until that time, until that I want to say 4.1 second, 0.41 second. You must wait until that time. So what you need to do, you see in the equation there is kV. You please plug in 345. Just that number. Don't convert into volt here. Then you will be getting wrong result. That's why it is written kV in that way. Just what is the kV value? So 345. So therefore, what you are getting 345 and you are dividing 34.5, meaning that you are getting 10. So therefore 10 plus 10.5, 20.5. So 20.5 cycles. This means a fault arc will be deionized after that time, after 20.5 cycles. So then convert that cycle into time with respect to 50 Hertz. So did you all get the same number, 0.41?
Yes, sir.
Yes, Dr. Ali.
Okay. So this means that one cycle equal to 20 millisecond based on 50 Hertz, 1 over 50, you'll be getting 0.02 or 20 millisecond. So therefore 0.41 second. That is the arc deionization time. This means after that, it is now safe to reclose the breaker. Now the question is, what will happen if you reclose the breaker before that? Because still the fault arc is going on. And if you reclose, then the current magnitude will be very high. It might happen that the fault current magnitude is much higher than the first time fault occurrence. So in real practice, it has been shown that someone has tried to reclose the breaker while there is enough ionization. This means fault arc is persisting. So this means you are putting more water into the fire. So therefore it will be much more blazing. So fault current magnitude will be higher. Okay, so there are 2 or 3 more questions, then you are done for today. What are the conventional times for opening, reclosing, and reopening the circuit breakers following a fault on transmission or distribution lines in a power network? So, I mean, we are looking the optimal reclosing technique. That's a technique, and it has better performance than the conventional. That is fine, but for the conventional system, what is the standard opening time? When you will open the breaker after fault happening, and when you would reclose. And if the fault is permanent, then you need to reopen the breaker. So what are those time? So when do you open the breaker? For example, fault happened right now. So from this moment, how much later you have to open the breaker? What is that time?
Within seconds.
Within 5 cycles.
Yeah, yes.
Yeah, everybody remember, within 5 cycles. Just note down in your note that fault occurs. Then within 5 cycles, this means maximum delay is 5 cycles. So then you can guess how long is the 5 cycles. So for 50 Hz system, it is 0.1 second or 100 millisecond only. And why is that 5 cycle? Because circuit breakers means protective relay. It has that controller and then trigger coil or the relay coil. Fault happened, and then circuit breaker should understand with the help of relay that fault has happened, and then it takes some time to get it open. So that's why maximum time is 5 cycle. Now there is very fastest circuit breaker, like I have seen in some example, at 1.5 cycle circuit breaker can open. 1.5, that is the fastest so far I have seen. Typically 2.5, 3, and then maximum is 5 cycle. So that's why if you are asked this question, you have to answer for the conventional approach, opening time is within 5 cycles. And then after opening, then breaker got opened, and then you have to reclose it. And then we learned that we have to wait because the fault arc should be deionized. Then of course there is wait time. So what is that wait time? I mean, what is the, again, reclosing instance? How long is that duration?
30 to 40 cycles.
Right. So for you are right. So you can say like in some country it is reclose after 30 cycles. So therefore you can write, and then the latest is the 60 cycle. So everybody please write down the reclosing instance is 30 to 60 cycles after circuit breaker opening. After circuit breaker opening. This means that first after, within 5 cycle circuit breaker open, and after opening, from that open moment, then you have to wait at least 30 cycle. So therefore earliest is 30 cycle and latest is the 60 cycle. Therefore please write down between 30 and 60 cycles breakers should be reclosed. Meaning that power engineers from experience, they have considered that okay, at least 30 cycle, that is enough to deionize the fault arc. That is the meaning. Now, as I was telling that MLGW or reclose after 45 cycles after opening the breaker. Once I had a chance to ask them, they said 45 cycle. But some countries, some power network depends on 40 cycle, 45, 50 cycles And then at the latest I have seen 60 cycle, and then earliest is 30 cycle. And then reopening, why it is asking reopening, you reclose the breaker, whatever after 30 or 40, 45, 60 cycle, and then the circuit breaker understood that is still the fault is persisting, still the fault is going on. So therefore again circuit breaker will reopen. So what should be that reopening time? Again it is another 5 cycles, like the first approach. Fault happened and then circuit breaker opened within 5 cycle. You reclosed, but reclosing circuit breaker understood, and the signal came that again the fault is going on. So therefore again, with the help of the relay, it will reopen. That reopening time another 5 cycle. So you can say after reclosing, reopening is within 5 cycle, and this reopening is applicable for the permanent fault. If it was temporary fault, for example, as an engineer, you are working on power line and you just made a short circuit and you realize that you are not doing right, immediately you clear the fault, or a bird was flying and created the fault between short circuit between two lines or all three lines, and then bird flew away. So meaning that those are the temporary fault. But reopening is coming. For example, stormy day, a tree has fallen and it is creating short, I mean, two line to ground fault or three line to ground fault, single line to ground fault. The meaning that the fault is going on, that is called the permanent fault. I mean, permanent means not like year after year, unless the operator or crewman from the power plant goes, the tree will not be removed. And that time might be 1 hour, 2 hours, 3 hours, who knows. So that's why once you reclose the breaker, and if the breaker understood with its controller that no, is still something going on wrong, and then again it will be reopened. That reopening time after reclosing within 5 cycles. So those are the conventional approach, I mean, which is prevailing all over the world, those technique, opening, reclosing, and then reopening. So the next question, in a power network consisting of synchronous generators, what are the main causes of time delay even when the system is at steady state condition? Like why I am asking this question, that even though system is in steady state condition, you remember the last class when we are looking the effect of time delay, we took an example that fuzzy control braking register, and that braking register needed the input which was the total kinetic energy. And we noticed that to calculate the kinetic energy, there is some time delay involved.
Mhm.
That's why I am asking that, for example, there is no fault in the network, but still there can be some time delay. So what can be the reasons? What are those causes for those
Use-
time delay?
Using the GPS to get the speed from the synchronous generator.
So so what are the devices? I mean, what are the synchronous generator common devices? Those like AVR, those governors, power system stabilizer, and there are some voltage regulators along the line throughout the network. So there are some devices connected in the system. There are some filters, even high size, big size, power filters along the line. So those will cause some delay. Those are the reason of the time delay. Even the system is a steady state condition. Therefore, once there is transient situation, transient stability or voltage stability or load change, something happen, and you want to initiate some controller, whatever it is, braking register or StartCom, SBC or any energy storage device, then those devices require some input for its functioning, for its control operation. And that time, the additional delay will come in the process. And if it's a hugely interconnected system and you need to collect total voltage or total kinetic energy or total active power or speed information, then there will be additional delay. So therefore, during steady state condition, those delay are not big because system is running fine. Those steady state delay has not that much impact, very little impact. Once you want to collect a global variable, that time it will have some impact. So therefore, you can say the main causes of time delay during steady state, the steady state devices, which are the typical devices, primary control means used in the system, like AVR, govern node, some voltage regulator. There are lots of inductance, capacitance connected, this capacitor bank. Those will cause some delay. Okay, so then okay, just a moment. You see, everybody see there is one question here. The figure one, this is the figure one. This is called IEEE 30 bus power system with auxiliary device, such as braking register. Now, what are the auxiliary devices? Like braking register is one of the example. I mean, it can be other devices like STATCOM, energy storage, SBC. It can be any devices aiming at the transient stability improvement of the system. There are two coherent group of generator. Can you see? Like I have marked by red color. This is on group, and then bottom this is other group. So before we discussed what is coherency, meaning that the generator which swing together, which shows very similar load angle or speed profile. So therefore, for example, in this case, number G5, G6, G5, G4, G3, these four generators, they have similar characteristics. And then bottom two generators, they have other characteristics, but similar characteristics. So in that way, we have clustered or grouped together two sets. That is fine. And hence, two auxiliary devices are connected near generator G1 and G6. Now, for example, this is one group, one coherent group. So meaning that the region of coherency is system reduction, so that you don't need to put one control device at each and every buses. So that's why this is one group. I put one control device, auxiliary device. In this case, it is near generator G1. And in this case, although there is G3, G4, G5, G6, you see, auxiliary device is put nearby generator G6. So the question is that how have those two locations been selected? How it was selected? Okay, we have to put one here and one nearby one. So the question is, cannot the devices be placed near other generators? What is wrong if I place it near generator G2? Or in this case, because I am saying that this is coherent group, this means all four generators behave almost equally. So what's wrong if I put this on here, or if I put this on here, and if I put this on here? So that's the question. So the first of all, the coherency helped me reduce the system size. It helped me analyze the system. We got the benefit. Another benefit of having the coherency, we can place few auxiliary device. And then the specific question, like among G3, G4, G5, G6, why this place is chosen? And between these two places, why the G1 is chosen, not the G2? So what is the reason? Like how those locations have been selected? So now this question, now of course, the question is, cannot the devices be placed near? You can place, I mean, near here, or you can put here, here, here. So what will happen? Now you see, this stability index equation, before we discuss the WC equation, this equation, this is a transient stability judgment criteria. So now, before placing any device, in real practice, what is done? You calculate the WC. For example, you consider a fault in the system. For example, here there is a fault, here there is a fault, you consider a fault. Or every system there is on severest point, you assume the fault there. And then you calculate the WC. You calculate the WC. The here and here as well. And then now you calculate the WC with respect to the fault for each and every generator terminal buses. For example, you assume that the fault is nearby that generator. You assume that the fault is nearby that generator and look the effect of all generator. You consider one fault at a time, but you analyze assuming that there is fault at each and every generator terminal. And then you look these numbers, these index, WC. So where the WC value is the highest, it is in G3 place or G4 or G5 or G6. So therefore in this system, for this specific IEEE 30 bus system, it has been seen that if the fault is nearby G6, then that generator provides the highest WC value. This means that G6 generator is the most vulnerable among those 4 generators. Accordingly, auxiliary device has been placed there. Because it is the most vulnerable, the WC value goes much higher. So now if you put here and here, this generator or this generator will be fine, but this will not be fine, even might go unstable. The same thing, if you consider fault here and here, and if you calculate WC, it has been found for this system, when the fault is nearby generator 1, its WC value is higher than this one. Accordingly, this place has been chosen. So and then it has been shown. And now you can argue, okay, you are putting auxiliary device near generator G1, but you are not putting anything. So it has been found through simulation, lots of simulation, that okay, the generator G2 becomes stable if you put it here. But if you put the auxiliary device here, then this is not unstable in some cases. The same thing for the upper system, upper group. If you put here, then that is fine, but other generators were not fine. So that's why you must put here. Therefore, because this is the most critical position, this G6 generator, you must stabilize this generator. And if it settles down, then after some oscillation, this generator will come back. So now, of course, again, you can argue, what is wrong if I place, I mean, instead of analyzing this, checking WC, what's wrong if I place auxiliary device at each and every generator terminal bus? Of course, you can choose, but what is the issue you guess? By placing the each auxiliary device, your cost will increase. Of course, the stability performance will be the best if you can put on auxiliary device at each and every place. Of course, even you can place here, these places, whatever the braking resistor or start com or other device. Of course, stability will be the best, but the cost will increase and increase. That's why there is this concept, coherency group. But then again, inside the coherency group, because there are several generators, so then instead of putting many auxiliary device, just choose one location, and you have to make a study which is that severest location in this group. So therefore, you need some judgment criteria. This is your judgment criteria. You need to look that number when it is giving the highest WC corresponding to fault here or here or here. And then you pick up the highest number and then put there. And then after that, it is not done then. After that, you check, okay, I put on here, and then again initiate the fault. And then look the status of other generators. That by placing the auxiliary device here, of course, it will help this generator, but what is the situation of other generators? Therefore, if you found that no, with little oscillation, the all generators are coming back in a stable position, this means then this is fine. So then now if you see that, okay, placing the auxiliary device nearby generator G6, this generator becomes stable, but like this one or this one somewhat unstable tendency, then choose another one here. So it might happen that you need to put two, not just one. And because here there are only two, you don't need to do either this one or that one. That will be dependent on that stability index criteria, which is giving you the worst number or the higher number. Where is the stability level is worse. So in this case, it was this one. So that's why in this system, only two auxiliary device is fine. Then like it is cost effective system and very optimized system. Everybody, could you follow me?
Yes, Dr. Ali.
Yes. So therefore, similarly, for example, if your research is about, okay, you have a IEEE 30 bus or 39 or much higher system and put some control means, for example, energy storage, then accordingly you have to choose the location, where to put the device, because there are many locations. So that's why you need some criteria. This is that judgment criteria. That's why this equation is very well known equation, because again it is, it is again capturing the W total kinetic energy information. That's why the WC value, stability index value that we'll be getting, it gives much better result, close to accurate result, perfect result, because it is capturing the information of all generators. So that's why it is helping me to the location where to put the auxiliary control means following a disturbance in the system. Okay, so with that, as I said, that I will not go much new things. After exam, I will start that fault current limiter. There are several types of fault current limiter. DC fault current limiter, AC fault current limiter, bridge type fault current limiter, parallel resonance fault current limiter. We will be looking superconducting fault current limiter. There are various types. So we will be looking those and how they help improve the stability. So we will be looking after your exam. So is everybody fine?
Yes, Dr. Ali.
Yes, Dr. Ali.
Okay. So therefore everybody please be ready for the exam. As I said, I think class 10 through 17. 17 means today. So therefore, right after the class, I am going to upload. I will make this video YouTube and then I will upload. And I think I already uploaded this one. You can see I already uploaded, I think few hours back, this lecture material until this slide. But I am going to upload the video right after the class once it is done into YouTube. Okay, so and as I said, you remember, although I have written down this time, but keep in mind, you can see the exam paper under the tab exams exactly at 5. So a little bit before, I think about 5 minutes before, I will be uploading. So then you are ready to start exactly at 5. You just download that one and then you start answering. And then as I said, please don't wait until 8. Don't assume that until 8 p.m. you will be writing and then you will be run out of time, because Dropbox will be closed. So I must recommend each of you that you try your best to finish all the answer at the latest by 7:30 p.m. And then you allot 30 minutes for scanning and making the PDF and then uploading. So then you will be fine. But if you start like 7:55, for sure you will be run out of time. So please don't do that. Everybody please start, or once you are done, you just upload. Okay, so with that, thanks everybody.